You guys have web space? Oh, huh. Sorry.
We have a classmate to like make one, but
I'm just kidding. I know you don't. I don't either. I purchase my own. I host my own. I mean, I spend like $7 a month for my website because I don't. I mean, Dr. Wang at various points has tried to get the university to let him have web space, and he's given up, I think. So anyway, it's whatever. But here's a picture of a parabolic path, and here I've actually graphed the velocity vector and the acceleration vector. So I mean, this is, you know, I'm just illustrating one of these deals, you know, like that. That's a parabolic path, right? Constant acceleration downward. Here's actually a graph of the position, the velocity, which is always right moving and sometimes going, always tending towards going down. The acceleration is negative and downward. And the acceleration is always constant minus g. That's what the thing looks like. I just think it's nice to see a picture of these things. I think the vector approach is really superior than just looking at formulas like we do. I'm not going to test you guys on this because it's not in your book, and I haven't really dedicated. I haven't given you guys homework, which helps you to really unwrap these ideas. We'll do this in Calculus 3 if you stick with me and you pass. Let's see here. You're here. You're going to pass. That's actually kind of true. I mean, if you're in class right now and working on problems, the statistical likelihood that you will pass is greater, right? Now, there's a person or two missing here who probably is fine. And maybe they're watching later because they're busy, like they've got some sort of online gaming that they're doing, and you know they have other time obligations. Their team needs them or something. I don't know. I'm not sure what you guys do, but circular motion, the acceleration, center seeking, and well, for constant speed. Getting to a point here. So there's the arc length formula we've been playing with. Of course, it's also distance traveled. If you think about what's the actual distance traveled, well, that's arc length, right? Displacement. Getting to a point here. Here would be acceleration around a circle where you didn't have constant speed. You could have a bit of tangential acceleration. There's always a centripetal piece, but if you're speeding up as you're going around, you can also have a piece of the acceleration which is tangential. But you've got a whole physics course to play with that, right? So I won't belabor it in here, but it is calculus to work it out. Again, I will get into details in Calculus 3 there. What I really wanted to show you was, for kicks, I calculated the arc length for parabolic motion starting at not necessarily the origin. So here I'm starting at x naught, y naught. So we're talking about, you start here. And then parabola like that, right? So what would be the arc length of that? We just worked a specific case of that essentially over here. That's a specific case of it. So, you know, to calculate the arc length, I have to integrate the speed, which here is just that, which gives me this. I make a u substitution, I get to this. And then I make a hyperbolic sine substitution. You can see it's kind of the same integral we're doing over there, just with constants in it, right? Because I make a sinh substitution, it gets me to this. And then I use that, and there you go. This is straight up the arc length of a parabola that, well, I'm not done yet. Sorry. Not done yet. I'm almost done, though. So there you go. This is the formula for the arc length of a, like this would be, if you wanted me to tell you how far, you know, if I was to throw this, for example, how far does this go if I just do this? If you could tell, if I could have told you what the initial speed in the x and y direction was, you just calculate this, that'll give you the arc length. So I think I'm assuming I come back to the same y value in this formula, maybe. It's got to be something like that. Otherwise, there should appear an x naught and a y naught in the formulas as well. Yeah. But anyway. Usually, for specific numbers, I would just do this integral numerically, guys. Like honestly, if I'm on the job somewhere and I have to calculate this, I'm not going to show my boss, hey, look, you can make this substitution and find this particular number. No, I'm going to pick an appropriate mathematical software. I'm going to calculate this numerically and be done with it. Because my boss should be very annoyed if I spend an hour to calculate it carefully. Now, on the other hand, if I'm setting up a model where there's some variability and I want to describe all possible ways we could configure the model, then maybe I want to do it by hand so I can actually find a formula which the variability in the formula describes what's possible for the setup, right? It kind of depends on the nature. Are you trying to build something that's adjustable, or are you just trying to solve an isolated specific problem? Isolated specific problems seem to me to be more appropriate for just a straight numerical method, you know? But what do I know? I don't know. Oh, marker. All right, well, you guys got more questions? Bring them tomorrow, I suppose. And save some of your energy for after the next test. We still have one more topic past this stuff, right? We cover differential equations, about 3 days, 4 days. I forget exactly how many days I've allotted. But you will need to study that and learn it. That's probably 10% of your final or something. What's that? That's a good question. I haven't thought about it.